Hi there. So the paper that we are going to talk about today is Maximum Entropy Inverse Reinforcement Learning by Zeibart et al. This paper is like the base idea of so many other papers in IRL. Papers like guided class learning, adversarial inverse reinforcement learning, they all share the same idea of maximum entropy. So if you want to understand them, you have to know the idea of why we use maximum entropy and what is using maximum entropy for inverse reinforcement learning in a discrete MDP. I'm going to give a basic explanation of why it's necessary and what was the whole idea, and then I will try to explain the algorithm. I'll try to be as explanatory as possible, but if there was any questions, please ask. So let's start with maximum entropy reinforcement learning. Maximum entropy inverse reinforcement learning and the whole inverse reinforcement learning idea. So basically, inverse reinforcement learning is the inverse of reinforcement learning. In a reinforcement learning problem, in the traditional version, we have an agent who tries to learn through a known reward function. So the reward function is known, and the agent, based on that reward function, tries to learn how to act, tries to learn a policy. But in IRL, we have a complete opposite approach. We assume that there is no reward function here, and the agent tries to learn some sort of behavior, like there is a behavior from the expert, and the agent is trying to learn what is the intention of that expert, what was the reward function based on this demonstration or based on this behavior. As an example, consider like a cook, a chef here, who is trying to make a croissant, and then there is a robot who is trying to learn from the demonstrations of this chef. Now, the difference between imitation learning and inverse reinforcement learning is the idea of reward function. In imitation learning, the agent is trying to learn a policy. What is like making this croissant, baking it, or doing something with it. But when the agent tries to learn the reward function, even if there is a change in the world, even if the croissant turns to become a donut, the agent will still try to cook it, try to do the thing that it was the intention of the chef. That's the whole idea. Now, these experts act to optimize, like the assumption is that the expert is trying to act in a way that is optimizing an unknown reward function. So this reward function is normally assumed to be linear in the features, at least in the context of discrete world, at the context of classic MDPs, not in the deep version. So it's normally considered to be a reward function that is linear in the features, and there are some weights, like it's the preferences of the expert for each of these features. And the whole idea is trying to learn these weights. What are the weights that make these demonstrations to appear normal? There is an ambiguity in IRL. The problem is that there are so many reward functions that explain the agent's behavior. Like, consider a whole reward function of 0. It will still explain the agent's behavior. Well, obviously, any demonstration can be shown to be an optimal for a reward function of always 0. And the challenge is to pick the right reward function from these all possibilities. Now, what was the Zeibart et al.'s approach here? They used the principle of maximum entropy to solve this ambiguity. Why? Because of this. So the entropy is basically how uncertain you are about something, and trying to remove, like by maximizing the entropy, you're basically trying to remove the bias towards something. As an example, if you have a 2-class variable, like a coin, you are flipping a coin. If you are 100% sure about it, your entropy is 0. If you're 0% sure, like if you're sure that it will not happen, your entropy is still 0. But if you're in the 50-50%, your entropy is in the highest because you are completely unsure about it. Now, when faced with uncertainty, when you're trying to maximize the entropy, this maximum entropy principle suggests that you are trying to choose a distribution that is most spread. Like it says, I don't know anything about it except for this specific constraint. And in our case, the constraint is the expert's demonstration. So you're saying, okay, I have 5 demonstrations. I don't know anything. I don't know which of these demonstrations are more important. I just take these 5s as my constraints and I try to be as unbiased as possible. I don't know anything and I'm trying to maximize my entropy here. This is why the idea is important in RRL and it makes sense. Now, why this is useful? Because this maximally spread distribution doesn't make any strong assumption except for the provided information. And in the RRL context, this avoids overly guessing what the expert is trying to achieve and instead trying to find a reward function that supports the observed behavior very broadly. So what is the setup of our RRL problem? First, we have the state space and action space. So we have an environment where the agent is acting. We have a bunch of states and a bunch of actions. And also we normally, at least in discrete environments and in the first classical version, we assume that we have access to the transition function of our environment. Later on the deep versions, we can assume that the dynamics is unknown, but for now we stick to the version that we know that transition function. And next we have some expert demonstrations. So we are collecting a set of trajectories from the experts that show this behavior, the expert's behavior. These trajectories can be not complete, like maybe they ended before the expert reaches to the final. So we are giving a chance to the suboptimal experts as well, but still they should be from some experts. And finally, we have some feature expectations. Now, what are these? For example, in a taxi driving task, these features can be something like the distance traveled, the time taking, reaching the destination, etc., etc. And based on how important each of these features are for our expert, there will be multiple weights for them. But the features, we have to have them. So there is this feature engineering is still a problem here. However, there are a bunch of features and we want to average over the features of the experts to take the feature expectation to see if I have like 100 trajectories from my expert, what is the feature expectations overall in these 100 trajectories. And now let's go to the paper to see it more in the mathematical view. Okay, so our reward function is we have the features that we defined earlier, and then the reward function is basically like some weights multiplied by these features. So it's just like a linear function of the features that each of the feature has a specific weight. We have our trajectories from our experts, and if we average over if there are m experts and we average over the features of these expert trajectories, we will get the expected empirical feature count, which is basically like the expectation over features for the experts. Next point is this feature expectation matching. So in their paper, Andrew and G and Russell, they mention that the feature expectations should match for the expert trajectories and the policy that this learner is trying to achieve. And they mention that this is something necessary and sufficient, even though it still needs lots of work, but this is the condition that we take for our maximum entropy optimization problem. So this is like the constraint here. So it says the probability of a trajectory multiplied by the multiplied by the features of that trajectory should be equal to the expert feature expectation. So we're trying to match the expectation over the features of a trajectory. This is like the formulation of an expectation. The probability multiplied by the event itself should match the expert's features. Now, in the maximum entropy IRL, the authors suggest that the plans with equivalent rewards should have equal probabilities, and plans with higher rewards are exponentially more preferred. That's why they use this exponential function. So it's like e to the power of reward divided by a partition function is the probability of a trajectory to happen given our weights. So any path that has a higher reward is exponentially more probable to happen. However, this partition function is like something that normalizes this probability, and it's quite hard to reach, and normally it's the challenge when it comes to the deeper versions, but here it's easy. It's just a summation over all of trajectories, but still. So each trajectory, the probability of it to happen is e to the power of the reward of that trajectory divided by a partition function. The next important things to know is this gradient function for our weights, because what we are trying to achieve here is the weight of our reward. We are using a gradient-based approach to reach that theta. Basically, the gradient of our loss is to match the feature expectations. So we are trying to match the features of our trajectory to the features of the expert. And the difference between these two is our gradient step. So this F tilde is basically our expert's feature expectation. And we can kind of simplify this by using something called a state visitation frequency, or DFSI, which says what is the frequency that each state has been visited. And if I multiply this by the feature of that state, I basically reach to this thing. So this is a gradient step in our problem. Now that I have found my gradient step, I need a way to calculate this D, because I already have access to this F tilde. It's from my expert demonstrations. I have access to this F of SI, which is the features for each single state. The only thing that is unknown here is this DSI. So I need a way to calculate this. And that's where this algorithm 1 comes handy. The algorithm is basically like this. We initiate a theta, a parameter, an initial parameter for our reward function. And then based on that new reward function, we try to reach to a policy, which is this backward pass. We can either use a regular method, like a value iteration, like imagine it as a normal RL problem. I have an initial theta, and then I try to run a normal RL, a normal value iteration on that theta, and then reach to a policy. Or we can use this partition function approach in order to reach our policy. In this case, in the case of using partition functions, we say that the probability of each action in a state is the partition function of that action divided by the partition function of that state. And this state is just the summation over all actions. This is exactly the same as value iteration, except for like a little twist that instead of using the values, we are using this e to the power of reward. And next, after we reached our policy, which is the probability of each action in a state, we try to run the forward pass. So with this achieved policy, now we try to recursively just make some trajectories with this policy, and then try to reach to our state visitation frequencies. So if I have my initial state visitation frequency, which is the initial state probability, I try to recursively compute this DFSI for my time horizon. This can be something like n, based on my policy that I achieved here or achieved in the value iteration formula. And this one is like my transition probability for my state. So it's like I have my initial state visitation frequency, and then I try to use my policy. So right now I'm in state 0. Based on my policy and my transition probabilities, this is the probability that I will go to state 1, state 2, state 3, and then I can have an estimation of what is the frequency that I'll visit that state, that next state. And I can just add it here. And based on that, I can have my DFSI. And finally, if I sum over all DSIs in my time steps, I will reach the state visitation frequencies. And this is exactly what will go inside this equation 6. And based on that, I'll have my gradient step, which I'm going to use it to do one step of optimization on my theta value. And then after updating the theta, this will just repeat itself again and again and again. With this updated theta and my updated Zeibart, I will do another value iteration. I will reach another new policy. Based on this new policy, I will reach a new state visitation frequency, and again and again. That's the whole idea of maximum entropy inverse reinforcement learning.